So earlier today, I talked about just sort of a general introduction about the geometry analysis and auxiliary geoms and landing gear and how those work together to create a bunch of a capability. And so now we're going to circle back around and we're going to, retread some of that information. But this time, since we have that context, we'll be able to dive a little bit deeper and things will make sense. So to start with, what you may ask yourself, why add an explicit direct component landing gear model in OpenVSP? And so there's a lot of good reasons in my mind to do this. First and foremost, there's a lot of analysis we want to do with a landing gear. And if we just use a generic stack or a generic other component, then we don't know, quote unquote, in the computer science way, we don't know that that's a landing gear. So by making it a landing gear component, I can build real intelligence, not artificial intelligence, into the model of how it is. Also, I'll just say that having a credible landing gear solution adds a lot to a conceptual aircraft design. I've seen a lot of aircraft designs over the years where people have spent many, they've killed many CPU hours in the pursuit of their design. And you look at it from the back of a room and you're like, yeah, the landing gear doesn't work on that at all. There's no solution that airplane balances and can take off and land. And, the more you get into a design, the more that matters. So having a credible gear solution adds a lot. And then what I was really trying to figure out here is okay, what can I add without adding too much complexity? We want to capture the design space and the importance of the gear, and we want to capture what it does to the airplane. But at the same time, at this point, I don't want to put a full kinematics engine into OpenVSP. And so there was a big debate that I had about how am I going to represent the landing gear? What is the right representation? And, when I think about it, the analysis that I want to do, i.e. the verb, what I want to do with the landing gear, determines the modeling detail. What I want to do determines what I need it to be represented. So, for example, if I want to do ground handling, then I need to know the contact points. What are the contact points on the ground? If I want to do tip back analysis, I need to know, where the wheel axis is, where the bogie hinges, and I need to know the static tire radius. If I want to do rollover analysis, I need to know things like flat tire radius, inflated radius, and the strut expansion and compression to do that kind of rollover. If I want to do packaging of the landing gear, well, then I need to get more into the gear mechanism design. And, spoiler alert, we're not doing that yet. We've decided we're not going to do the packaging. But then there's a lot of different sort of levels of detail we could go for. I could just do landing gear, could have just been a ground plane and 3 contact points. And that could have been the landing gear model, right? That would have been a start. We could start to model the tires in the down position, maybe up and down position. And maybe we start to put in the strut and the bogie in terms of some of those things. Then we could go further than the strut and the bogie to include secondary struts, different pushers and things like that, and actuators, all the way to things, the real nitty-gritty details like the up locks and down locks and how does the real mechanism work. So, I debated a lot of these things and, what was appropriate at a conceptual design level. What I came up with, and then there was also this debate that I had with myself of, should I come at this with what I call sort of a top-down model, meaning we start by taking a strut and we attach it to the aircraft at a trunnion, and then at the end of the strut, we put an axle with wheels on it, and then from wherever the wheels go, we then determine where the ground plane is. So that's a top-down. We go from the airplane down to the ground. Another alternative is what I call the bottom up, where we first define the nominal ground plane, and then we position the wheels on it. And you may or may not even need a strut then. But if you did, the strut would then go up and, maybe it would connect to the airplane, maybe it wouldn't. Or maybe there's sort of a middle out where you start by positioning the wheels in 3D space, and then the ground plane is intelligently figured out where that is based on where the wheels are. And again, what do you do with the strut in that case? So there's different pros and cons to these. And, it comes back to sort of what we talked about with a routing geometry the other day about, well, the update sequence. How does OpenVSP update a model, and what does that mean? What does this mean for attachment and all these things? So the TLDR, I went with the bottom up. So we used a bottom up approach for the landing gear. And right now, there is no strut in the model. I have some ideas that maybe someday we could add that. But for now, maybe this is going to be surprising, but the gear doesn't retract and it doesn't have any struts. So the general approach is that we have, and then there was also the choice of, do we want to do with separate geometries? One geometry for the main, one geometry for the nose gear, one geometry for the ground plane. And do we model all these separately? Or what we went with is a combined. So we actually have, it's sort of this combined component that's all the landing gear in one. It's based on the ground plane, but it also contains all of the different bogies and all the different tire definitions. So that's that combined approach. So I went with a combined approach from the bottoms up, and we left out the strut is sort of the decisions that I've made. So in the gear component, there's the design tab, and if we were to talk about starting with the transform tab, what the XForm tab of the gear component really is controlling is the ground plane, the nominal ground plane. So this is the idealized, where's the ground in relation to your model, and the XForm tab positions that. And when you go from there, then you come over to the design tab and you start adding bogies. You start adding groups of wheels and you position them in XY on that ground plane. So you're positioning them where they are on the ground. And you can also specify the Z above ground. So if you have something like a U2 or a B52 where you've got an outrigger that's out on the wingtip that does not normally in the nominal wings level position, does not normally touch the ground, you can do that. You can have your gear that touch the ground, and then you can have other gear that don't touch the ground. So we've got this, fundamentally it's a ground plane representation. We can either automatically choose that size where it'll choose how big of a ground plane to draw based on the size of the model, or you can dial it in yourself if you want to tune that. And you can also decide whether or not to draw that ground plane. All the analysis works whether the ground plane is drawn or not, and no matter how big you have it. The analysis is independent of that, but just for visualization, you can control whether you want to see the ground plane or not, and whether you want to see its extent. This component needs to know the units of your model. And the reason is because tire designations are given in inches. The standardized international standards for tires are given in inches. And so if you're going to specify a tire in inches, then for me to draw it in the right scale, I need to know what scale your model is. So we do that right here. You tell it what units your model is in, and then you can specify your tires in inches, and everything will work out. And then the last thing that the gear actually has is it has a full CG envelope. So the min, the max, and the nominal CG position in both X, Y, and Z. And so we're going to draw that as a little box with a dot in the middle. The dot's the nominal, and then the box shows the limits. And importantly, right, this is not calculating the CG of your model, right? We have a mass properties calculation that if you go and spend a bunch of time and you specify the densities of all your airplane, it'll do a bottoms up calculation from the geometry of what the CG must be that matches that. This is the opposite of that. This is I'm the conceptual designer and I dictate my CG needs to be here, right? We're just waving a wand and placing the CG. And we're also therefore defining the envelope. So there's no math that determines this other than you dictating where the CG is. But we need to know the CG in relation to the gear in order to do those tip over and tip back type calculations. Okay, so that's how the overall gear design. Then we drill in and we talk about the bogie design. And so you can place as many bogies as you want. Usually you'll have two, a nose and a main, with the main being reflected symmetrically. So you'll end up with 3 contact points. But if you don't want the mains to be symmetric, you can do that. You can drop them from that. If you want to have more, like a wide body, like a A380 or a 747, where you've got multiple main gear, you can add multiple main gear. You can add bogies like a B52 or whatever. So you can, you add your bogies, as many as you want. And then you dial in the configuration, which is how many wheels across and how many wheels in tandem there are. And so in this case, I'm showing a 2-2. And if you weren't aware, there's an FAA designation, a standard for that a 2-2 is actually represented for a 2 duplex. And so the configuration up here, I actually write that. I write a 2D. So there's a 2 duplex, or if you go to a triplex or whatever, a quad, this configuration represents that FAA designation. So then you can dial in, the spacing between them, either side by side or longitudinally, whether you want to specify that as a gap or a dimensional distance between them, so you can dial those things in. You dial in the position of the gear relative to the ground plane. If it's a steerable wheel, you put in the maximum steering angle. So if your nose gear can turn 90 degrees, you put in 90. If you can turn 20 degrees, you put in 20. Your mange, you'll leave that 0. The strut deflection, it's a very, very simple model of strut deflection. All it is a direction vector, a magnitude of compression, and a magnitude of extension. And that's how we model, in this case, how you specify what the gear travel and the strut compression and extension is. It's just a vector and a magnitude in each direction. Same vector, different magnitudes potentially. And then we have limits, constraints on the Bogie rotation. So if your gear has a maximum, say the Bogie can only rotate 10 degrees, then you can put in here and you can put in that plus or minus 10 degrees for the Bogie rotation. And when I'm doing the calculation for things like the tail strike, if the tail strike angle is greater than 10 degrees, then the Bogie will rotate for the first 10, and then it will rotate about the wheel's axle until it finds the tail strike. So it'll do all that geometry to figure out when the tail strike happens with that kinematics. Okay. So that's how we lay out the Bogie, and then we can talk about the tire. And so what I did for the tire is there's a professional society called the Tire and Rim Association, and they set the standards for tire nomenclature and how people talk about tires and a lot of other things. And you can search for the Goodyear or Michelin tire handbooks. So this one, I don't remember which one I grabbed this from. It looks like the Michelin man in the corner. So they'll publish PDF files with tables of tire data, and that's all based on a parametric geometry description. So I went ahead and I paid for basically copies of the standards for the Tire and Rim Association, and I used that to build a parametric model of the tire that matches the TRA's documentation. And it's completely massively overkill, but it was a lot of fun. So I actually have the rim curve here and the tangency of the tire hitting it. It's completely over the top. So that's always fun. So on the tire, you choose which Bogie you're editing, the active Bogie, and then you can put in the tire designation. And typically that'll be in inches. You'll put in what the diameter and the width of the tire are in inches. If you don't want to work in inches here, then you can work in the model units. And so you tell it the model units instead. You tell it the ply rating. This is only used for the grown wheel dimensions. We could talk about that as later. So you can put in that ply rating, or it's used for this sidewall detail shaping it. So it doesn't matter much. You can play with it if you want, but it's just there. And then you dial in the rim parameters. The diameter of the rim the width of the rim is a part of the designation. The diameter of the rim is a part of the designation. So what you see up here, this is 44.5 by 16.5-21. So that's a 44.5 inch diameter by 16.5 inch width by 21 inch diameter. So here on the rest of these parameters, we have, instead of just 2 options, you can either specify them in inches, which will match the data from the handbook if you're looking something up. You can specify them in model units if you really want to stick to your model units, or you can specify them as a fraction of either the diameter or the width. And so for most of these parameters, in particular, this 0.77, 0.82, 0.88, and down here, the 0.35, these are very representative numbers that are non-dimensional, that are going to represent a lot of tires. So for the most part, you're really only going to want to change diameter, width, and diameter of the rim, and dial those in to match your tire. And the rest of these, you can tune them if you want, but mostly these non-dimensional settings are good. Okay. So that's all about setting up the nominal ground plane and the nominal landing gear definition. We then need a whole bunch of different kinds of auxiliary ground planes. So these are, again, used by the geometry analysis for setting up these off nominal ground plane positions. They also, if I have a landing gear with 3 contact points, I need to tell it, well, which contact points, which axle am I rotating about when I do something like, my tail strike calculation. So I have to tell it which points we're rotating about and what's the off nominal state of that gear. And so that's what these auxiliary ground planes are for. And in the auxiliary geom, I'll show you that in a bit, you have the choice up here where you can choose many different kinds. So rotor tip path, rotor burst, and then we have 4 different landing gear types. We have 3-point ground plane, 2-point ground plane, 1-point ground plane, and then we have the 3-point composite clearance envelope, which is that interesting aircraft carrier one I talked about. So you choose your type, and what you see here is the different analyses that they're used for. So if you're doing the 3-point ground plane, that's what's used for the ground and steering clearance, the weight distribution, and the ground maneuverability. The 2-point is for the tail stripe and the tip over and the tip back. The 1-point is for that roll clearance when you're on one wheel and you're seeing whether you hit the nacelle or the wingtip first. And then finally, the 3-point composite clearance envelope, that's its own, it's a 3-point, but that's that aircraft carrier one. And now each bogey then, if you have 3 bogeys, you then have the ability to come in on each one. You tell it which contact point. So you pick for an auxiliary geom. You say, oh, I want to use the nose and the main, and I want one contact point to be the 0 symmetrical copy and the other contact point to be the 1 symmetrical copy. So you set that up, and then you can tell it on the suspension. Do you want the suspension to be nominal, compressed, or extended? And then do you want the tire to be nominal, extended, grown, or flat? So these are different states for the tire. And what's amazing is for a simple tricycle gear that is a symmetrical tricycle gear, there end up being 720 possible off nominal states that gear can take. So there was really a sort of a combinatorial explosion that we're trying to handle by setting up these auxiliary geoms. So you dial that in that you want, and then you go and you add your geometry analysis. And so there's a bunch of different geometry analyses. And each one of these then needs a specific auxiliary geom, and it needs specific primary geom as well. So the yellow ones in this list, this is a table of all the geometry analyses currently in the development version of VSP. And the yellow ones are what we're interested in right now because they're the landing gear associated ones. And so what this table means is, for example, if you want to do a tip back calculation, then you need to tell it a 2-point ground plane. And this is the tip back from the CG. So it knows then the 2-point ground plane, and it knows the CG from that landing gear, and you don't need any secondary geometry. So it can do that tip back calculation knowing just the 2-point ground plane. If you want to do the tail strike angle, then that's going to be, you're checking interference with the plane, you're checking interference with the ground plane with a 2-point pivot point, so 2 contact points on the ground, 2 landing gear, and then you're finding that angle. What's that tip back angle? So the plane 2-point angle is another analysis type. The primary geometry is what's the geometry you're trying to find a collision to. So that's going to be the rest of the airplane, and that can be a mode or that can be a set, but it can be that geometry. So that'll be that any type is the primary. And then the secondary is going to be a 2-point ground plane, right? So basically this table tells you, and everything should make sense when you understand what it's doing, that, a weight distribution, you need to know all 3 points on the ground. For the sideways tip over, for the tip over maneuverability, you need the nose and the main contact points. So all these dial in what geometry information is fed to the analysis. And as I talked about earlier, there's a whole bunch of gear-related geometry analyses. We've got our tail strike angle, we have our CG tip back angle, our tip over angle, our ground maneuverability, our roll strike angle, and then less familiar to people, maybe the composite clearance envelope. And so if you want to specify what is the envelope that you're interested in, that's a special separate text file. which looks like this. And all it is just 2 columns of X and Y data. In here, I've started at -1,000 and come across and then specified out what these points are. And when you read in this file over here, you actually have to tell it what units the file is in, because just like everything else, now you're bringing in something with dimensional information into VSP, which is normally non-dimensional. And so in this case, my file over here is in inches, and that's what I know my clearance is in, but maybe my model is in feet. And so I have to tell VSP, yes, I read in this file, but then that file should be interpreted as if it's inches, and then it'll be scaled properly. And then we have this definition of the main gear offset for it being imperfect. And that becomes a surface that we can check. And so while that's up, I'm going to go ahead and fire up and do a little bit of a demo. And anybody has any questions, please go ahead and ask them in the chat, and I'll try and address them as best I can. And actually, before going to the transport, let's start with an empty model. And we'll start by just adding a landing gear. And you'll see that when we first add a landing gear, all we have is a ground plane. So, we start with a ground plane. As I said, its position, its origin is wherever it is in the transform. So I'll move it around in a minute, but right now we'll just start with it at the origin. So we have a ground plane, and as I said, right now we're automatically sizing it, and without anything in the model, we just size it to 10 units, and we're drawing it. If I don't want to see it, I can turn it off. My model's in feet, and of course my tires will be in inches. And my CG, I haven't specified any CG yet. So it's all just 0, 0, 0. And that's that gray spot right there at the center. So if I want to add a bogey, I just come over here and I add, and in this case, we'll give it a name. We'll call it nose. I didn't have a name at first, so let me rename that. So this is now my nose gear. And I want to move its contact point forward. So we're going to bring that out to say, we'll call it -10. That positions that nose gear. And, I can come in now, and I'm showing it pretty coarse, just like anything else. I can increase the tessellation to make that look a little prettier. I can come in here, and if I want, 2 or 3 or 4, however many wheels across in that landing gear, I can do that. And then likewise, now you wouldn't normally do this on a nose gear, but, if you wanted 2, 3, 4, however many wheels in tandem, you can dial that in. So we'll do 2 across and 1 in tandem. And then, like I mentioned earlier, we can either talk about it in terms of the gap of the spacing is a gap. So how far apart are these in terms of a gap? Or, we can do it either fractional or in model dimensions, or we can talk about the center distance. What's essentially the pitch, the distance between centers of these. So, if you're reading off a print, you may have that read off as a center distance or whatever works for you. Okay, so we've got, our contact point. Right now, our compression direction, that's what this green line is in the background. This is showing me, spacing gap of 0 is a little bit little. The compression travels, so that's showing me where my compression would go. So this is the bogey pivot point, is that center point there. And if I compress the gear, it's going to move that all the way up to here. And likewise, the extension, if I extend the gear, it's going to move it all the way down to there. So this just depicts, and if I move, for example, if I change that vector, right, I'm dialing in some X component to the vector. So I'm just showing, how does the, what is the unit, the direction vector of compression and the magnitude there. And that's visualized with that green line. All right, I'm taking way too long here. Let me just go ahead and add in another bogey for my mains. And you can see it's back here. Let me give it 2 across and 2 in tandem. And let me move that, out in the Y contact point. And then in this case, I'm going to want to say that it is symmetrical. So I've got a button here to say it's symmetrical. So now I have a typical tricycle gear. So that's what adding a landing gear is like. We can come over here to the tire, And again, on a per tire basis. So here we are, we're on the nose Bogie. We can say, you know what, that's too big. This is only going to be, say, a 10-inch tire. Oh, I'm missing it. Sorry, that is the main. Let me rename that. Sorry. There we go. So in fact, we don't want that to be 10. We want that to, say, be 20. So we can dial in and change that size and, dial in the tire size. And I will say, notice when I'm drawing this, notice the tire sticks a little bit below the ground plane. And that's because the nominal ground plane is what we draw. The tires are all drawn at the static loaded radius with respect to that ground plane. Okay, so that's how we set up a nominal landing gear. What we can do then is we choose that landing gear and we choose an auxiliary. And when I add that auxiliary, I then have to come to the design tab and I choose what kind of auxiliary. And obviously, a rotor tip path is not a meaningful auxiliary for a landing gear. So in that case, we're going to come in and say we want to use a 2-point ground plane. So this would be something we'd use for like a tip back angle. So we choose, or let's start with a 3-point. So we're checking clearance with the ceiling. So we choose a 3-point ground plane and it immediately draws what is that off nominal plane. But we want it defaults, right? We have nose gear. So we want to make this nose, and then we want to choose the main and the other symmetrical. So now what we have is if I show only, I'm now drawing the off nominal landing gear. And you'll notice its tessellation is different, right? It has its own tessellation control if I want to make that fine. It has its own tessellation control. But so this is now drawing the off nominal landing gear. And so I can come in and I can specify what's the state of any of the gear. So let's take this landing gear and say it is now compressed. And so now you can see that it jumped because the left gear was compressed. And we can make the left tire, say, flat. So that means it's going to ride on the rims. And so that's how you can control what an off nominal gear state looks like. And if I show them both, you can see how that movement is, right? So we have the nominal gear position and then that off nominal. So that's what you do to set up and use all of these. Again, I'm behind schedule, but let me jump over to the transport model that has all these things set up already. And what we can see here is, right now, I'm only showing the nominal gear, right? And for all these auxiliary geoms in this particular model, I'm not actually, like my 3-point ground here, it's also everything's nominal. So now I'm viewing it, I still have everything nominal and static load, but I needed this, for example, this 2-point ground mains. Let's just, let's show that one and let's turn off that other one. Come on, there we go. Turn that one on and let's turn off the nominal. So notice the nose gear is gone, right? That's because the 2-point landing gear doesn't have the nose gear in it. And so this is just the main. So then this is what we're going to do that tip back calculation about. And again, I'm running out of time, but if we come back to the geometry analysis, the way you set all these up is you add one to add it. That's going to show up as default. You need to choose the type. So in this case, we want it to be a planar interference with an angle about a 2-point rotation. So that's plane 2-point angle. And so then we're going to choose our primary geometry as, say, the airframe as a set. So we're going to compare it against the airframe. And then our secondary is going to be this new, what do we call it? 2-point ground mains. So 2-point ground mains is going to be what we rotate about. So that's what we do to set up the tip back. And then we can evaluate that. And notice it already did it. It calculated that tip back. And notice we have some options down here because we were rotating in, by its sign convention, the counterclockwise direction. So if we wanted to rotate the other way, we would calculate about that. And we would see that in this case, this geometry is going to hit the nacelles first. So that's its rotation there. So that hopefully gives you an idea of how you set up the main landing gear, the auxiliary landing gear, and then the different geometry analyses. I'm going to delete that one. And hopefully you're going to have to go back to the slides, I think, and look at that table to make sure that you see how things map in terms of which analysis you need in which case. but I think it should make sense. Everything, has to be the way it is. And so if you understand what it's trying to do, you should be able to see and think through the process. So I know that's been a bit of a fire hose and fast, but I'm going to try and stay on schedule and jump back and then talk about the rest of the geometry analyses.